Hi everyone, my name is Faris Antaki. It's a pleasure to be talking to you today about large language models in ophthalmology. We often think of AI models through the lens of supervised learning, where we train a specific machine learning model on labeled data and deploy it for a very specific task. For example, in the context of language, this can be text generation, text classification, or question answering. Foundation models, on the other hand, are a novel paradigm for building AI systems. They differ from traditional machine learning models in their approach to learning. They are trained at scale on large amounts of unlabeled data through self supervised approaches. A single model can then be fine tuned or adapted to perform a multitude of tasks all at once. Foundation models can be made for language or for vision. They can also be made for both. Multimodal models combining both language and vision capabilities are likely to be most beneficial for us in medicine because they reflect the inherent nature of how we practice, where we rely on history and examination to manage patients. Today, the most popular foundation models are large language models or LLMs. LLMs are fine tuned foundation models that generate responses in natural language. They are trained on vast corpora from the internet, including archives and millions of books, as well as encyclopedias like Wikipedia. To understand how they work, let's take a simplistic example of one way they can be trained, using a famous quote from Heraclitus, a Greek philosopher. The only constant in life is change. Parts of the original text are masked, for example, the word change. A transformer model is then trained to predict the masked word in an effort to minimize the loss or difference between the original text and the predicted word. Predicting the word growth would require the model to adjust its parameters until the word change is predicted. This process is repeated using billions of words at scale. Those models, through a concept called attention, are capable of handling sequences of data, sentences, in a way to understand the context of each word by considering it in relation to all words around it. In this way, LLMs effectively learn how we write and how we speak. But how we write and how we speak in our collective written corpora, particularly in the vast and often anonymous world of the internet, frequently contains inaccuracies and errors. And more concerning, it may contain themes of discrimination and hate speech. So, an LLM, before being released to the public, must be aligned to our values. In general, it is agreed that LLMs must be helpful, honest, and harmless. In medicine, the stakes are high, and we must look at the outputs of LLMs in a holistic manner. Beyond quantitative measures like accuracy on multiple choice exams, we must look at answers and validate the presence of incorrect information, the agreement with scientific consensus, the omission of content, the extent and likelihood of harm and bias. This evaluation framework is inspired by a seminal paper on the subject published by Singal and colleagues in Nature in 2023. That same paper evaluated the performance of Palm, an LLM that is fine tuned for medicine and language, for its capacity to answer USMLE style questions in medicine. In fact, LLMs have shown very strong capacities in answering this type of questions, and they are continuously getting better, not only in general medicine, but also in ophthalmology. In 2023, we published seminal work in ophthalmology science, followed by a publication in the British Journal of Ophthalmology, where we showed improvement of GPT-4 models in answering ophthalmology questions. GPT 3.5 scored around 50% in January 2023, and 6 months later, in July 2023, the performance increased significantly to more than 70%. However, it's important to note that when we present those data and those findings, we're presenting a snapshot of results at a given time. These findings may not generalize due to changes in the models over time. In fact, it's becoming more and more evident that Evaluating LLMs is a minefield. Performance is highly related and tightly related to the prompt used, the model settings and temperature, as well as the model version and training cutoff date. Now, beyond medical question answering, there are many potential use cases of LLMs in ophthalmology. Broadly, they can include medical education, workflow improvement, and clinical assistance. Imagine a virtual teacher that is able to generate multiple choice questions based on guidelines. A student would prompt it to generate a question about a specific topic in an active learning fashion. Or a documentation agent that can record and summarize a clinical encounter and write a note in the electronic health record. And of course, a smart triage agent that would answer patient queries and analyze patient images 24 hours a day, 7 days a week. But for LLMs to see and understand images, they would need to have vision capabilities. LLMs with vision capabilities are also known as vision language models, VLMs. VLMs have most potential in ophthalmology, in my opinion. Here's an ideal example. An ideal model would support interleaved text and multimodal patient imaging. The output would ideally contain a diagnosis and explanation, and then the ophthalmologist would be able to further prompt the model to get more information on treatments and prognosis and even generate a report for the EHR. However, commercially available LLMs and VLMs like ChatGPT and Google's Gemini model, in my opinion, might never have specialist level knowledge of ophthalmology. And as such, we might need to leverage other techniques to gain more benefit from those models. For LLMs, we can leverage custom instructions to indicate to the model how it should behave and how it should respond. And more importantly, we can leverage something called retrieval augmented generation. This may improve the output of LLMs by grounding the model on external sources of knowledge like ophthalmology textbooks and guidelines to supplement the LLM's internal representation of ophthalmology. While this may solve the language problems of LLMs, the vision capabilities of VLMs must also be at the specialist level. And to reach that level, we might need to build bespoke foundation models with strong computer vision capabilities. And we're already starting to see the rise of those foundation models with RedFound, the first ophthalmology foundation model that was built here at UCL. The ideal scenario would be to have a model with strong vision capabilities, and I believe this will likely be bespoke. The language capabilities might come from a generic model and be improved by techniques like retrieval augmented generation using vetted, trusted consensus information. The future of LLMs in medicine is promising, and this is only the beginning. Thank you.